Hello, everyone. Welcome. My name is Cory Levels, and I am a technical consulting engineer here at Intel. I'm very excited to get the opportunity to present to you all today and talk to you all about Intel Advisor, specifically the optimization and prototyping of code with Intel Advisor. Let's jump straight in here. So quick agenda. Today, we want to talk about a lot of the key features of Intel Advisor. We're going to start out with a little bit of optimization for CPU with the Intel Roofline feature, then get into all of the different vectorization features of Intel Advisor, then shift gears into offload modeling, and lastly, we'll go kind of full circle back to the Intel Roofline feature, but for GPU instead of CPU. A rich set of capabilities for high-performance code design. Intel Advisor is a performance analysis tool that is capable of doing a lot of different things for your applications. So what you're seeing on this slide is just kind of a high-level outline of the key features that we're going to talk about that fall underneath that Intel Advisor umbrella. We only have about 45 minutes planned for this presentation, and we definitely want to leave time for a Q&A at the end to hear from you guys and address any questions you guys might have on the content you'll see today. And for that reason, we'll primarily be focusing on the first three outlined features on this slide. So we have Offload Advisor, which is going to be a feature of Intel Advisor that will allow you to identify the portions of code that would be profitable to offload to a GPU and can even predict the code's performance if you were to run strictly on a GPU. And it will allow you to experiment with all kinds of different accelerator configuration parameters. We'll also go into detail on roofline analysis. A roofline analysis is ultimately going to offer you a very efficient way to characterize your kernels and visualize just how far you are from ideal performance on your specific system. And lastly, we'll go into detail on vectorization optimization. And this is going to be a big part of Intel Advisor. It's going to tell you which places of your code are vectorized or not, how efficiently they're vectorized, and for the regions that were not, it's going to tell you exactly why the compiler was unable to vectorize those regions of code. And just to briefly touch on the last two here, we've got thread prototyping, which is going to be a feature of Intel Advisor that's going to be able to analyze which pieces of your applications should be threaded, and then can predict performance if you were to implement that threading. And lastly, building heterogeneous algorithms, specifically referring to the flow graph analyzer, RFGA. And that is a feature that at a very, very high level is going to allow you to visualize your data flow graphs and can create those dependency graphs for you. And with that, we'll get into our first agenda topic, the CPU roofline with Intel Advisor. I think this section is best kicked off with what is a roofline chart. So a roofline chart is a method of visually overlaying your actual application performance onto representations of the hardware limitations for your specific system. So essentially, this chart can be used to identify not only where bottlenecks exist, but what's likely causing them, and which ones we're going to provide, which loops are going to provide the most speed up if optimized. Plotting a roofline chart. So here we have just a simple kind of outline of a roofline chart to go over this a little bit more conceptually for you guys. So what this roofline chart is doing, this is charting the application's achieved performance and the arithmetic intensity against the system's maximum achievable performance. So we can see here, x-axis is the arithmetic intensity versus the y-axis, which is going to be the performance, in this case, the flops. But if I turn my red laser pointer on here, what we want to draw your attention to is this diagonal dark blue line. This is what we're referring to as a roofline. These diagonal lines are going to represent the memory bandwidth limitations that are preventing your plotted loops and functions from achieving better performance. And also these horizontal dark blue lines, those are going to represent your compute capacity limitations. So the idea here is that a plotted loop or function, which is representative of the dots, a plotted loop or function cannot exceed the topmost roofline, as this is going to represent the maximum capabilities of that specific machine. So ideally, the greater the distance between a plotted loop or function and the highest achievable roofline, the more opportunity there is for improving performance for your application. So if we see here on this simple outline of a roofline chart, we can see this plotted loop or function has less room for improvement, as in less headroom to reach that compute capacity limitation versus the plotted looper function down here, whereas this has a lot of room for improvement to hit that top roofline. Ultimate performance limits. So here we have another outline of a roofline chart. But what we want to illustrate here is that a roofline chart is very useful in determining whether you're memory bound or compute bound. So we can see here, we've got our diagonal memory bandwidth lines, limitations, and if a loop is plotting underneath those memory bandwidth rooflines, you can conclude that you're memory bound, versus if they're plotting underneath these horizontal compute capacity rooflines, you're compute bound. Identifying good optimization candidates. Here, we're going to keep building off those last couple of slides, just kind of going over roofline conceptually. And we want to note here that the sizes of the plotted loops and functions are going to correspond with their levels of impact. So the large red plotted loops and functions, those large red dots essentially, are going to be where advisor is saying, hey, this is where you want to spend time. This is where you're going to get the most return on your optimization efforts. The yellow plotted loops and functions, they may be useful to optimize. You may see some noticeable improvements, but it might not be worth it, or it could be situational. The green dots, the green plotted loops and functions, those are going to be what advisor has determined to have very little impact on the optimization of your application. Also, another thing I think is really illustrated on this visual here on this slide is that the idea that a roofline chart can help you identify your primary bottlenecks, like we mentioned a couple of slides ago. We can see here on this example that we have some scattered loops and functions that have been plotted. And when you're looking at your data, your primary bottleneck is going to be whatever your closest roofline is to each plotted looper function. So we can see here our plotted looper function G, that closest memory bandwidth limitation, that diagonal line, that's going to be our primary bottleneck for that loop. CPU roofline example. As you can see here, we have some actual results to show you guys. This is what a CPU roofline looks like in the advisor GUI. These results are from a simple matrix multiply example. Actually, all of the results you'll see today in my presentation are going to be from the same matrix multiply example that is available to you all in the official OneAPI samples repository. But we can see here on the top half of the screen is the roofline chart with our diagonal memory bandwidth lines. We can see our L1 bandwidth, our L2 bandwidth, our L3 bandwidth, and a DRAM bandwidth. And we can also see our horizontal lines, our compute capacity rooflines, and a couple of plotted loops. Like we talked about a little bit earlier, when we're looking at our data, we want to spend the most time looking at the big red plotted loops. Again, that is what advisor is drawing our attention to and saying this is where you're going to get the most return for your optimization efforts. We can see here that we have one, and it's actually plotted underneath the DRAM bandwidth roofline. So just at a first glance, we know we're DRAM bound, not even using the cache. Before we even want to look into vectorization, we really need to address that DRAM bandwidth roofline. And if we look at the bottom half of the screen, we can see that the source code corresponding with the plotted loops and functions, and some inline comments that an advisor will provide. And as well, to the right of that, you'll see some metrics from that loop, like the total time, the loop and function time, and the traits. Vectorization with Intel Advisor. The right data at your fingertips. What we have on this slide is a visual of the part of Intel Advisor that's going to give you a lot of information surrounding the vectorization of your application. So when you open your results in Intel Advisor, you'll be defaulted to this summary page on the left-hand side here. But if you just jump over to the Survey and Roofline tab, this is where you can find all of this information about your application. So just at first glance, when you look at this section of Advisor, you can see things like the loops that Advisor has determined are good candidates for optimization, what is preventing vectorization for certain loops, just how efficient your code is overall, the vector instructions that were used, and any vectorization issues that may be present. We've actually gone ahead and put together what we consider to be 5 steps of efficient vectorization. So number 1, compiler diagnostics, performance data, SIMD efficiency information. So this is going to be kind of referring to that last slide. It's just going to be some information on where you are right now in terms of vectorization of your application. Just kind of a snapshot of where you are currently. Number 2, guidance, detecting problems, and recommendations on how to fix it. So advisor is going to give you a lot of guidance on why you weren't vectorized and maybe where you were poorly vectorized in your application. Number 3, precise trip counts and flops and masks, understanding utilization, parallelism, granularity, and overheads. This is going to kind of tie into number 1 here. It's just going to give you a little bit extra information on the current state of the performance of your application. So, how efficient your application is and how well those vectorized loops are performing. Number 4, a loop carried dependency analysis. So this is going to be for looking into those loops that were unable to be vectorized. And there are a number of reasons as to why a loop may not be vectorized, and we'll get into that in the next couple of slides. And lastly, number 5 here, memory access pattern analysis. And this is just going to be possibly using this to look into those already vectorized loops, and just looking at the memory that they're accessing. Efficiently vectorize your code. So kind of going back to number 1 here in a little bit more detail. So the compiler is going to generate that optimization report. You can pass the compiler flags that is going to make it strictly a vectorization report. We will recommend that you use an Intel compiler for this because I think that can just generate a little bit more useful information when you're using Intel Advisor. But those optimization reports or that vectorization report is going to help advisor fill in a lot of this information in figuring out why the compiler was unable to vectorize certain loops. We can see in this case, in that top loop there, it's detected, a possible vector dependency. So because the compiler is always going to play it safe. It could be looking into different things, and it's always going to lead on the side of not vectorization, if not vectorizing, if there's anything in question here. So here we can see a possible vector dependency, but there are a number of reasons, right? So it could, the compiler could not vectorize because it thinks the gain is going to be too low, or it could not vectorize. It only vectorizes inner loops by default. So again, there's a number of reasons as to why the compiler could be unable to vectorize a certain loop. And you're going to get that reason in this why no vectorization column here. Now, if it was vectorized, you're going to be able to see a nice breakdown of information surrounding the vectorization of those loops. You're going to be able to see the instruction set, the efficiency, the gain, the vector length, a lot of the compute performance information as well. So, and number 2 with guidance, this is the section of Intel Advisor that you'll find those recommendations and that guidance to really help you understand things like where it's going to pay off the most to vectorize, quickly identifying, what's blocking your vectorization. It's going to give you tips for effective vectorization, and it's going to kind of help you, guide you to safely force that compiler vectorization and optimize your memory stride. So we can see this column here titled performance issues as well, tying into number 2 here. This is going to be where you'll see some of those recommendations as well. And you can also come down to the bottom half of the screen, and there's a recommendations tab you can use to also get a little bit further guidance and details. So in this particular case, we're seeing that this top loop was not able to be vectorized because there was a possible vector dependency detected, like I mentioned. So if we see that information, we can go down to this recommendations tab, and we can clearly see advisors saying, look, we have we've detected a possible vector dependency. We played it safe. The compiler did not vectorize this loop. We need you to look into this a little bit further. So we're going to actually recommend that you go ahead and run a dependency analysis on this particular loop. So number 3 here, so these precise trip counts and flops and masks. I mentioned that this is kind of tying into step 1, but it's just some additional information on the current state of the performance of your application. So if you can see the trip counts, it may help you understand where you will get the benefit of optimization. So for example, we can see this highlighted loop here, the bold loop on this slide, may have a call count of about 4,000. So we can see the call count about 4,000. But what we can conclude for that, so we may consider optimizing this loop, right? But what we can see here is that it's taking up so little of the total CPU time that we may be able to conclude that the initialization of this array may not be worth our time to optimize. is it safe to vectorize? So number 4, those loop carry dependency analysis. So like we mentioned, we detected a possible dependence, vector dependency, and that's why this loop was not vectorized. So what we want to do with that information is we want to take that and we want to say, okay, now we want to look into this loop a little bit closer. And Intel Advisor is going to help us with that. So what we can do is run a loop carry dependency analysis on that loop. So it's very simple with Intel Advisor. All you want to do is check the box next to the loop, and then you come over to the left-hand side of the GUI, and there is a start button for that dependency analysis. And depending on the results of that dependency analysis, we can conclude or not whether it's safe to vectorize. Now, if it comes back with no dependency found, then you can feel confident in adding that pragma to your application and going ahead and moving forward with the vectorization. And the dependency analysis will give you more information on those pragmas to insert in your applications. And then you can rebuild, run through Advisor again, and hopefully see your updated results. Advisor memory access pattern. So number 5 with the memory access pattern analysis. This is going to be the last step in the 5 steps of efficient vectorization that we've been talking about. This is going to be looking at the inefficient memory access patterns and how they can be improved. Also, this can kind of tie into understanding why you're memory bound and getting some next steps for optimization. So take our matrix multiply application, for example. We saw in the beginning of the presentation with our CPU Roofline results that the application is memory bound. Remember, it was plotting underneath that DRAM bandwidth limitation, so we concluded that we were memory bound. So now what we can do is we can come over here with that information and we can run a memory access pattern to get an understanding as to why we're memory bound and get some possible next steps. So if we look at our memory access pattern results from this matrix multiply application, and we can see we have a footprint estimate of 31 megabytes, access pattern of mixed strides, a strides distribution of 67%, 33%, and 0%, corresponding with uniform stride access, constant stride access, and variable stride access. And we can come down to the bottom half of these results of this loop, and we can see that for this loop, we have a stride of about 4,096. So what we might conclude from this, looking at these results, is that we may want to get that stride down. We may want to make it smaller so that we can fit all of that data into cache versus having to go all the way out to DRAM. And hopefully that will improve our performance a little bit, because at the end of the day, improving data locality and your cache utilization will be more effective in improving performance than just vectorization. Now let's shift gears into offload modeling with Intel Advisor. So ideally, I think this is a tool for after you've optimized for CPU. And now you can say, okay, I've optimized for CPU. Now I want to get some projected performance on a target device, on a specific GPU. Because the idea with Offload Advisor is that you're able to measure your application's performance and compare it with its modeled performance on a selected target GPU so that you can decide what parts of your application you can execute on a target device. So what I'm going to do is keep it kind of consistent. We've got some projected results for our matrix multiply application, and I've got some screenshots for that to share with you guys. So Intel Advisor offload modeling. So here we can see we've got a screenshot of kind of the summary page as a whole. Quite a bit of information on this page, but we're going to break it down here section by section in the next few slides. But I think it's important to note what we really want to reinforce here with Offload Advisor is that it's going to ultimately help you identify which kernels to offload, predict your kernel performance on current or future GPUs, and identify any bottlenecks or potential issues. But we can kind of go over briefly the high level kind of sections on this page. So we've got our program metrics, our top offloaded section. This is going to be your offload recommended for offload, your loops recommended for offload, and your offload bounded by. And this is going to be those specific factors that prevent your code from achieving a better performance if it were executed on a target device. So getting into a little bit more detail in these sections. So program metrics. well, I guess we'll start with top metrics at the top of the slide here. So we can see our top metrics. This is kind of just a snapshot of overall how your application performed with these projected results. So we've got, the speed up for the accelerated code is 3.3x. The whole application is 3.3x faster on our target device. And this loop is going to take up 100% of the whole application's execution time. And it's identified a total of 2 potential offloads. Now, if we come down to program metrics, this is where you're going to view the main performance metrics of your program, such as number of offloads, speed up, and the time spent on the target device. And if you check out this bar chart here, what this bar chart is doing is it's visually comparing the original execution time spent on a base platform. So, for example, your CPU with the estimated execution time on a target device. In our case, the Gen 9 GT2. And this chart on the bottom left-hand side, that's going to be a breakdown of the estimated time by specific tasks. So we can see the program time on the host, the non-accelerated time, the time in the MPI calls, and the time on the target. So on the summary page, we saw kind of a snapshot of our top loops recommended for offloading to the GPU. But if we jump over to this accelerated regions tab, we're going to get a lot more of a comprehensive breakdown of those top candidates for offloading. So we can see here that our top loop recommended for offloading is going to be, last level cache bound, has a projected, has a projected 3.32x speed up, is estimated to run on the GPU for approximately 6.997 seconds. And we can see the offload summary, the throughput, and but what we really want to point out is that you'll be able to see your estimated data transfer here on this far right column. So as you're porting your application to a discrete GPU, it's really important to consider how much of your data will be transferred from your CPU to your GPU, and then of course back to your CPU. This data transfer cost can often dictate whether the GPU offload is even worthwhile for your application. So Offload Advisor is going to give you the data transferred, and it's going to use that in addition to other internal metrics in determining whether you should offload based on your specific GPU's characteristics. So another kind of building off that last slide here, so another kind of building off that in-depth analysis of your top offloaded regions. So here you can also see the source and call tree, and this is just, I think, a little helpful for seeing your top candidates for offloading in the context of the call tree. So our last topic for today is going to be our GPU Roofline with Intel Advisor. And again, similar to the CPU Roofline, it's going to show you if you're memory bound or compute bound on a GPU and how you can improve performance. Finding effective optimization strategies. So again, like we mentioned, very similar to CPU Roofline, but since Advisor has the capability to plot a Roofline chart like displayed here on the right-hand side, you're going to be able to visualize your application's performance levels relatively to the system's peak compute performance and memory bandwidths. So again, something we want to really reinforce here is that a Roofline chart is really helping you visualize your application's performance and visually see what's holding you back. So again, very useful for finding those high impact but under optimized loops. And it even helps you answer things with your application, things like, does my application need cache or vectorization optimization? So again, just reinforcing here some of these bullet points. So highlighting your poor performing loops, showing those likely causes of bottlenecks, referring to that closest roofline to your plotted loops and functions, and suggesting next steps for optimization. Finding effective optimization strategies. So here we have a little bit more of a cleaner screenshot for you guys to see, because there's a lot of very useful features with the GPU Roofline that may not be super obvious. So what we want to point out here is you can configure your levels to display. So you can see here you can do the different operations. So you've got your int or your floats. You can also show your memory levels, your CARM, L3, SLM, GTI. So, and also if you come down to the bottom, bottom screenshot here, you can see again going over that, showing that room, that performance headroom for each loop. So we can see here, we've got our, if you highlight the loop, you're going to get some of those metrics. You can see with this highlighted loop here, we can see the self performance, the self CARM arithmetic intensity, the self elapsed time, and the self memory traffic. And again, we can see that we have some room for improvement here to reach this next roof line. And again, showing those likely bottlenecks, next roof line closest to your plotted loop or function, and suggestions for optimization. Customized to display only desired roofs. So this is a very useful feature. I think that with a lot of roof lines, if you've got a lot going on with your application, these roof lines can get a little bit cluttered. So I think it's a good idea to keep things organized depending on what you're looking at that point with your application. It could be very useful to only display certain roof lines and hide other roof lines, or if you want to see all of the roof lines at once, you can certainly do that as well. But I think it's nice to be able to have control over exactly what you're looking at, and maybe be able to hide any roof lines that might not be relevant to what you're looking at that moment with your application. So our last slide here we have on the GPU Roofline with Intel Advisor is going to be some nice results that we've queued up here for you guys. Same application, matrix multiply application here. And we can see what a GPU Roofline looks like in the GUI. So we've got a few extra features here, like we mentioned, might not be as obvious, but still very, very useful. So if we look at the top of the page, we've got our summary metrics. If we kind of go to the right here, we can create a snapshot. So creating a snapshot is actually a pretty subtle but very useful feature. When you use this creating a snapshot feature, it's going to package up your binaries and your sources along with your result set so that you can copy it to another machine and still be able to view the source, so that this makes it really easy to share your results with someone else or move it to a different machine. And it's going to keep your sources all intact and very easily accessible. So now here we can see viewing the details, the GPU source, and GPU assembly information. We did not include a screenshot of that again, but I think it's pretty self-explanatory. You can see the corresponding source code, and it's very easy to flip back and forth with that feature. So GPU performance of compute tasks, again, you can see the compute task, the elapsed time, and that GPU compute performance breakdown as well. And customizable GPU roofline chart, again, going back to that very useful feature and being able to control the rooflines that you're seeing, having control over what you're looking at with those rooflines. Hiding certain roof lines or showing specific ones that are more relevant to what you're trying to achieve with your application. And lastly, you can switch between your report tabs like we've kind of been mentioning. You'll be defaulted to a summary page when you open up your Intel Advisor results, and you can jump over to these GPU roofline regions as well. A couple things we don't have pointers to on this slide. So this small roofline section over here. So this is kind of like a mini roofline, if you will. And what this is this is going to be corresponding to your left-hand side full-size GPU roofline. But if you highlight a specific loop or function, you're going to be able to see kind of a mini roofline corresponding to that plotted loop or function. And it's going to show you just kind of a little bit more breakdown of that plotted loop or function. So it's going to show you, what that is bounded by, and just exactly how much performance you're going to get if you can bump it up to that next roofline. And of course, you can see on the left-hand side of that roofline, we've got another little section here of our memory metrics, and that's just going to be a breakdown of how much time is spent at each memory level. So again, I think it's nice to kind of show you guys a GPU roofline as a whole in what it's going to look like in that Advisor GUI, and a little bit kind of high-level overview of a lot of these features that the GPU Roofline feature can provide for you and your applications. So that is all I have today for the GPU Roofline section and just kind of going over a lot of those key features of Intel Advisor as a whole. I hope you found some of this content useful. And with that, I think we can jump over into the live Q&A section. Thank you.